So this unit we're going to start getting a little deeper into polynomial functions and what is their behavior, what do they model, how do we solve polynomial equations, and all of these things. That's what we're going to be working on for the next 2 units. So just to make sure we have some common vocabulary, remember polynomial has many terms. We can classify polynomials in a couple of different ways. We can classify them by the number of terms that they have. Number of terms. You have heard me use these kind of terms before. We said a monomial has 1 term. Binomial has 2 terms. And a trinomial has 3 terms. And anything larger than that, anything more than 3 terms, we usually just classify as a polynomial, not a quadnomial or anything, just a polynomial. Anything with more than 3 is going to fall into that category. So we can classify it by its number of terms. So this would be one name that I could give a polynomial. Another way that we can classify a polynomial is by its degree. So let's talk about degree for a second. We can have degree with polynomials that have more than 1 variable. You can have x, y, z, all kinds of variables. What I'm going to specifically talk about, though, are just polynomials with a single variable. We're just worried about y equals and then just the x. That's what we want to talk about. When we talk about degree with just 1 variable, the degree of a polynomial is the highest exponent. So out of all the times that that variable shows up in the problem, what was its highest exponent? That's the degree of the exponent. So for example, if I have 5x to the 4th plus 6x cubed minus 7x squared plus 2x plus 8, if this is my polynomial, then the degree is 4. It's a 4th degree polynomial. We do have some names to go along with the degree. You can just call it 4th degree by the number, but we do have some names that go with specific degrees. A couple of warnings about degree. You do want to make sure that you're finding the highest exponent. For example, this one was in standard form. It went from the highest exponent to the lowest exponent. So we consider that standard form. So the degree is really easy to find when it's in standard form because it's the first degree. It's the first exponent that shows up because it's the highest. If it is not in standard form, however, you want to make sure you're looking at all of the exponents and make sure there's not like an x to the 8th down here out of order, and make sure you really are getting the highest exponent. So we have used some polynomials already. We have studied some polynomials already. For example, if it is a 1st degree, the highest exponent is 1. A 1st degree polynomial is a linear function. And we have studied linear functions. A 2nd degree polynomial is a quadratic function. We have studied the quadratic function. It's x squared is the highest exponent. A 3rd degree, so we're talking about x cubed. A 3rd degree polynomial is going to be a cubic function. So you see that as cubic. A 4th degree, so the highest exponent is x to the 4th power, is going to be a quartic function. And a 5th degree could also be called a quintic. And you may have also seen this on your graphing calculator. If you go in your graphing calculator, we've done stat edit and stat calculate several times. You'll notice that all of these polynomial functions, your calculator can do a regression for. It can find equations for. We've done linear, we've done quadratic, but you'll also see cubic, quartic. So we've got up through at least 4 on our calculator that you can do. There's other things there that we'll be doing as the year progresses, but your calculator can do polynomial regression up through at least quartic, the fourth degree. So that's what it is. Generally, anything larger than this, and honestly, anything larger than 3, I generally just go by the number. So 8th degree polynomial, 10th degree polynomial, or 12th degree polynomial. But these are a little more common, and they have been given some names. So you want to make sure that you can find the degree of a polynomial. That is one of the ways that we classify polynomials into families. Degree also tells us a lot about a polynomial. What is its behavior? Things about its graph. So one thing that we do want to know about the graphs, we're starting with the graphs of polynomials. All right, so things that we know about the graphs of polynomials. They are continuous. So they don't have any jumps or gaps or holes. Okay, so they are continuous functions. Piecewise functions can have gaps. We know that some graphs have asymptotes. Okay, a polynomial function does not have an asymptote. It is a continuous function. That's one characteristic of a polynomial graph. We know that they're smooth. Okay, we don't have any sharp corners or anything. Everything is nice and smooth and curvy. They can take different amounts of curves and different things, but they are a smooth curve and not like absolute value that comes to a straight point. You know, we don't have any points in a polynomial function. They are smooth. All right. And so then it is the equation itself that can give us some clues about what the rest of the graph looks like. So in particular, over the next few days, we're going to be learning about some different parts of the graph. How do we find the different parts of the graph? What are the characteristics of those different parts? Specifically today, I want to talk about end behavior. I'm going to talk about end behavior and terms. I can tell a lot about a polynomial graph just by looking at its equation. I don't have to type anything into a calculator or anything into Desmos. Just by looking at its equation, I can tell what the ends of the graph are doing. So these ends, these arrows, what are these ends of the graph doing? And I can also tell what could possibly be going on with terms. Now notice that I did say possibly. Okay, just by looking at the equation, I don't know everything about the terms, but I do know some things. So we know that with a polynomial graph, they have smooth turns because it is polynomial, and we know some things about the end behavior. So let's talk about those things. So with a polynomial equation, the end behavior is what are the ends of the graph doing. And when we talk about what are the ends of the graph doing, we're talking about as we go to the left, is the arrow increasing or decreasing? Is the arrow going up or is the arrow going down? And then as we go to the right on the graph, is the arrow increasing or decreasing? Is it going up or is it going down? There's several different ways that we do notation for end behavior. You can keep it very simplistic and say, okay, to the left, it's going up, and to the right, it's going down. Sometimes you'll see it with words. They'll say, as the graph goes left, it's increasing. As the graph goes right, it's decreasing. So we do want to think about up is increasing, and down is decreasing. But one of the things we're also working on this year is getting that formal notation. So I also want to show you what that would look like with all of our infinities and stuff like that. If you recall, we use negative infinity for the left and positive infinity for the right. We use negative infinity for down, and we use positive infinity for up. So one way that we could write it is as x approaches negative infinity. So when you see this statement, okay, the way we would read that would be as x approaches negative infinity. And the way you would want to translate this is on the left side of the graph. That's what this statement is saying, is what is the graph doing on the left side. So as x approaches negative infinity, comma, f of x, now remember f of x represents y, so we're talking about the y value, f of x approaches positive infinity. And so the way we would read this is as x approaches negative infinity, f of x approaches positive infinity. What that really means is the left side of the graph is going up. That's how I would read that. We could also do as x approaches positive infinity, so that's talking about the right side of the graph, then f of x is approaching negative infinity. And this would be how we would write down. So this is some notation for how we can talk about the end behavior of a graph. But how do I just look at the equation and know what the end behavior is doing? And so that's what we want to talk about next. So if I want to know what is the end behavior of a graph doing, I do need to look at the equation, and there are two things I need from the equation. I need the degree and the leading coefficient. So again, vocabulary, just to make sure we all know what we mean when we say leading coefficient. If a polynomial is in standard form, meaning that you have the highest exponent going first, and then you're counting down from there, then the leading coefficient is the very first coefficient in the equation. It is the coefficient of the highest exponent. Now, if it is not in standard form, then you either need to get it into standard form or at least find the highest exponent, that degree, and then you are looking at the coefficient of it. That's what we want to look at first, actually, because the leading coefficient tells us what the right side of the graph is doing. It is always going to give us the end behavior of the right side of the graph. Because if the leading coefficient is positive, then we know that the right side of the graph is going up. So the leading coefficient, if it is positive, then the right side is going up. If it is negative, if the leading coefficient is a negative number, then we know that the right side of the graph is going down. All right. So if it is increasing to the right, it is positive. If it is decreasing to the right, then it is negative. Doesn't matter whether it's a fraction, a decimal, a whole number, an even number, an odd number. That doesn't matter. What matters is whether it is positive or is it negative, and that's the leading coefficient. Now the degree doesn't exactly tell us what the left arrow is doing. It does, however, the degree gives us the relationship between the left and right arrow. So how do the left and right arrows relate to one another? So if we know what the right arrow is doing, then we know what the relationship between the left and the right arrow is. We can find the left arrow. So the relationship, the degree, now if you remember, the degree was the highest exponent. It's what we classified the polynomial as. So if the degree happens to be even, 2, 4, 6, 8, 10, 12, okay? So if it is an even degree, then we know that the left and right are the same. Meaning that if the right side is going up, then the left side is also going up. If the right side is going down, then the left side is also going down. They go in the same direction. If, however, the degree is odd, then we know that the left and right arrows are opposites of one another. So that means if right is going up, then left is going down. If right is going down, then left is going up. And so this is why you can see it doesn't exactly, like point blank, tell you what the left arrow is doing, but it tells you how the left arrow relates to the right arrow. So you always want to figure out what is the right side of the graph doing first. Find out, is it positive or negative? Is the right side going up or is the right side going down? And once we know what the right side is doing, we can then determine what the left side is doing based on whether it should be doing the same thing or should it be doing the opposite thing. So for example, if I have the polynomial y equals x cubed minus 5x squared plus 2x minus 8, and I want to know what its end behavior is. I do not have to actually go to Desmos and graph it. I can just look for the leading coefficient and the degree. So the highest exponent was 3, and don't forget, when there's not a number written in front of the variable, it's that understood 1. So this is my leading coefficient. My leading coefficient is positive, which tells me that my right arrow is going up. Positive, right arrow going up. Negative, right arrow is going down. Now to figure out what my left arrow is doing, I look at the degree. The degree is odd. That tells me that the left and right arrows should be going in opposite directions. So since right is going up, left should be going down. So always figure out what your right side of the graph is doing, then you can determine what your left side is. Don't forget formal notation for this. If we were writing this in formal notation, as x is going to the left, which is negative infinity, f of x is going to negative infinity, because on the left it was going down. And as x is going to positive infinity, that's the right, then f of x is also going to positive infinity because the right side was going up. So this would be our formal notation. So don't forget that. But hopefully you see how it is that you find it. Let's do one more example just to make sure. If I have y equals negative 2x cubed minus 4x to the fourth plus 3x plus 8. Okay? So before we jump to too many conclusions, the first thing I notice is it's not in standard form. So I need to make sure I get it in standard form. All right, so the highest exponent is actually 4. So that's got a degree of 4 and a leading coefficient of negative 4. So when I look at that, the leading coefficient is negative, so the right arrow is going down. Left, the degree is even, so they've got to be doing the same thing, so that means that my left arrow has to be going down. And so I can say that as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x is also going to negative infinity. They're both going down. So the right arrow is going down and the left arrow is going down. Make sure that you can tell why. Other things that we can tell just from the equation and just knowing what the degree is degree can also tell us how many turns that polynomial could possibly make. So if the degree is even, we know, as we just said, we know that the arrows have to be going the same way. All right? So if I've got the arrows going the same way, that does limit my number of turns. If it's odd, in order to get something to be odd, we know that the arrows have to be going in opposite directions. So, that could possibly give us a couple of more. The number of terms is kind of a fixed thing. So, there's a little, it's not a formula, but there is a rule that says the most possible turns, not terms, but turns, those sound very similar. The most possible turns a polynomial can make is one less than its degree. All right, so the most terms that a polynomial can make is one less than its degree. Let's talk about one that we're familiar with. We've done x squared, right? We've done quadratics. That's a degree of 2. 1 less than 2 is 1. That means that the most turns that a quadratic can take is one turn, which is why quadratics always, 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 always turn out to look like a parabola, because they can only make one turn. 1 less than 2 is 1. We know that its arrows have to end up going in the same direction, so having 0 turns is not an option. If it didn't turn at all, then one arrow would go up and one arrow would go down. So the only number of turns that a 2-degree or a quadratic polynomial can make is just one turn. If I have a polynomial that's, x to the 5th, however, 1 less than that is 4. So it could take 4 turns. So 1, 2, 3, 4. All right, that is the most it could do. It could not have 6 turns. That would be too many turns. The most it can have is 4. It is important to note, though, that this says the most possible turns. It can possibly have less turns than 4. However, that doesn't mean any amount. If it had 3 turns, 1, 2, 3 turns, then its end behavior would be wrong. Remember, it's an odd. It says that the ends have to be going in opposite directions. So 3 turns doesn't work. That wouldn't get its end behavior going in the right direction. However, 2 turns could be a possibility, because I could turn once, turn twice, and I'd still get the correct end behavior, and it is still less than 4. I could also, let's see, if we did 1 turn, though, again, that gets my arrows going in the same direction, and that's not going to fit the proper end behavior for 5th degree, so that's not a possibility. 0 turns, well, it goes and it doesn't turn at all, but my arrows could still end up in the same direction. So these are the possible turns that a 5th degree polynomial could make. It could make 4 turns, 2 turns, or no turns, but these are all of the possible amount of turns that a 5th degree polynomial could take. But to find the most possible, it's always just 1 less than whatever the degree is.